Today we'll talk about Chapter 6. Chapter 6 is the frequency response, Bode plot, and resonance. For the frequency response and Bode plot, we require that you understand the concept and then know how to calculate the frequency response and draw the Bode plot. For the resonance, I only introduce the basic concept. You guys only need to understand the general idea. Now first let's look at the signal. Signal in our class means either the voltage information or the current information. From what we learned before, for example, the Fourier series, we know any signal is the sum of sinusoidal component. Here you can see this example. The left graph is the music waveform, and the right-hand side is the sinusoidal component of this waveform. This sinusoidal component has different frequency and has different amplitude. Also, they may have different phase angle. We know that if you use the Fourier transform to analyze the signal, you may have the frequency information. You transform your signal to the frequency domain, and then you can see their component of the sinusoidal information. Now let's look at another example. The left graph is the square wave, and the right-hand side are the sinusoidal component of this square wave. If you look at the Fourier series, you can see the square wave signal can be written in an infinity series of the sinusoidal. For this sinusoidal component, they have different amplitude. The first one is 4a divided by pi, the second one is 4a divided by 3 pi, and the third one is 4a divided by 5 pi. You can see the pattern, and then you know that this is the infinity series. And also, if you want to look at the frequency information, you can see the first one is saying omega 0 t. The second one is the saying 3 omega 0 t, and the third one is the saying 5 omega 0 t. You can see the frequency, in fact, increase because we know that sin omega t, the omega equal to 2 pi f, so you can see the sinusoidal component for the frequency, they will increase. So we know that the sinusoidal component for this square wave, as the frequency increase, the amplitude, in fact, will decrease. If we look at this graph, you can see the fundamental frequency, which is the sin omega t, is this bigger one, the bigger signal, which has the least frequency. And the other two are the 4a divided by 3 pi sin 3 omega t, and the 4a divided by 5 pi sin 5 omega 0 t, so that you know this is the second sinusoidal component, which has the 4a divided by 3 pi, and the frequency is 3 omega t. And all these sinusoidal components add up, we are going to get our original signal. You can see this blue signal, in fact, is the summation of these 3 black signals. It's quite an approximation of the square wave. You can imagine if we continue to add the following infinity sinusoidal component, we'll finally get our square wave. In this case, you can see the fundamental angular frequency, the 4a divided by pi sin omega t, is the fundamental one. That means it's the basic one. It's the most approximation of this square wave. This table shows us the frequency range of selected signal. You can see the audible sounds is from 20 Hz to 15 kHz, and also the AM radio broadcasting is from 540 to 1600 kHz. The FM radio broadcasting is from 88 to 108 million Hz. Now let's look at another concept, filters. Filters in our class means circuits. The amplitude and phase of the component are altered in passing through the filter. So here, if you look at this graph, you can see if this is a two-port filter network. The two-port means the two terminal, like what we talked about in the Thevenin equivalent circuit. You can see the left-hand side is the input signal. The Vin is the voltage information here, and the two-port is for the input. And if you look at the right-hand side, the two-port is for the output, and also the output is the voltage signal. And when the input signal passes through this filter, then the amplitude and phase of the component will be changed. The change is based on the frequency. That's why we see that for chapter 6 is talking about the frequency response, because the sinusoidal component of different frequency, when they pass through the filter, their change, the amplitude and the phase will be different, so that we can choose the components we don't like to reduce their amplitude. For the signal that we want, we can amplify their amplitude. Then we can manipulate the sinusoidal component so that we can get what we want. Now let's look at another concept, which is the transfer function of a filter. As we said, for the signal, when they pass through the filters, they will change. Then how much will they change? It depends on the transfer function. The transfer function is defined as the output divided by the input, the voltage of the output divided by the input. So here, if you look at this formula, you know that they are in the border letters. That means they in fact are the phasor. So all of these three components in this formula are phasors. V out is a phasor. It not only includes the amplitude signal, but also includes the phase signal. The same thing for the input. They are the phasor, including the amplitude and the phase information. The transfer function is the division of the output and the input, so that the transfer function also is a phasor. It not only have the amplitude information, but also has the phase information. Here, these two graphs represent the information of the transfer function. The left-hand side is for the amplitude. The right-hand side is for the phase angle. If you look at the left-hand side, you can see the amplitude may change, depends on the frequency. If your signal's frequency is 1000, then the amplitude will be 3. That means you amplify your signal of the frequency of 1000 by 3 times. If your frequency is 2000, then you can see your amplitude is 2. That means you amplify your signal of 2 frequency by 2 times. But if your signal has a frequency of 3000, you can see here it is 0. That means if you have a frequency with 2500 or higher, then this signal will be filtered out. At the same time, when your signal passes through the filter, the phase angle also changes. So here you can see this graph means the phase angle changed as the frequency. If your frequency is 1000, then the phase angle will be 30 degrees. That means your phase angle will be increased by 30. If your frequency is 2000, then your phase angle will be at 30 degrees. Here, if you look at the pattern, you can see for the following frequency, the according phase angle will be changed. Now let's look at an example. Here you can see our input signal is 2 cosine 2000 pi t plus 40 degrees. And the transfer function will think as this is our transfer function. This graph indicates the amplitude change, and this graph indicates the phase angle change. So we first need to understand what is our frequency, because as we said, if you have different frequency, the frequency response will be different. When you have different frequency signal pass through the filter, then your amplitude and phase angle change will be different based on the frequency. Then here we know that cosine 2000 pi t plus 40 degrees, it has the omega as 2000 pi, and omega equal to 2 pi, so we know that frequency in fact is 1000 Hertz. And for the phase angle is 40 degrees, so that we know that our phasor in fact can be written as 240, which is our representation of our input signal. The input is 240, so that is our input signal in the phasor representation. Now, if we want to know what will be the output, we can look at this graph. We know that the transfer function equal to the output divided by the input. If we know the input, we multiply by the transfer function, we will know the output. So in fact, for the transfer function input-output, if you know any of the two, you should know the other based on this formula. For example, if we know the output and the transfer function, we can figure out what is the input. Input will be equal to the output divided by the transfer function. Okay, now let's look at our example. So we figured out that our input signal has a frequency of 1000. So we look at this amplitude graph. We know that the amplitude change will be 3. So 3 is the magnitude for the transfer function. And then we look at the phase angle. For the 1000 frequency, the phase angle will be 30 degrees. Then we know that the transfer function can be written as 330. So here you can see this representation is at frequency equal to 1000, the transfer function equal to 330 degree. And we know that the transfer function equal to V out divided by V in. If we know V in equal to 240, then the output signal will be equal to the transfer function multiplied by input, which is 670. The amplitude is 6 and the phase angle is 70. Here you can see our input amplitude is 2. After the filter, it has been multiplied by 3. It has been amplified by 3. So the output signal will be 6. And the original signal has a phase angle of 40. After the filter, it changed. It increased by 30 degrees. So the output signal, in fact, can be written in the sinusoidal form as 6, which is the amplitude, cosine 2000 pi t plus 70 degree. As we said, when you represent the sinusoidal signal, you have the amplitude, in this case is 6, the frequency information, in this case omega equal to 2000 pi, and frequency is 1000. You have the phase angle, which is 70. So the three components, the amplitude, frequency, and the phase angle, are the three factors of the sinusoidal wave. If we know these three factors, we know exactly what is a sinusoidal wave. Now, if you look at this example, you can see this sinusoidal wave pass through the filter. The amplitude and the phase angle will change, but the frequency won't change. The input signal is 2000 pi t, and the output signal is also 2000 pi t. The filters won't change the frequency, but the filters will change the amplitude and the phase angle based on the frequency. Depends on what is your transfer function. You can see at different frequency, your amplitude and phase angle will change differently. Just now we talked about if one signal passes through a filter, what will be the output signal? What if you have several components pass through a filter? How can we determine what is the output? Because as we said, any signal can be written in the summation of a series of the sinusoidal summation, so that we know any signal in fact have multiple components. So how should we process if a signal with multiple components? Now, first you should determine the frequency and phasor of your original signal. That means you read your original signal in the form of the phasor representation. Then you figure out the frequency for each of the components. As we said, the frequency response will be different for each of the frequency. So after you figure out the frequency of each of the component, you can determine what is the change of the amplitude and the phase angle. Then based on the frequency of each of the component, you can figure out what will be the output component for that frequency. Because we know that the output equal to the input multiplied by the transfer function. So if you figure out for each of the frequency what will be the transfer function, you can figure out what will be the output of that frequency component. Then after you figure out the output component for each of the frequency, you add all the component up. Then you will get your phasor representation of your output. Then after you figure out what is the phasor representation, you can easily convert it to the sinusoidal representation of your signal. Now let's look at an example. Here in this case, our input signal equal to 3 plus 2 cosine 2000 pi t plus cosine 4000 pi t minus 70 degree. So our signal in fact includes 3 components, which is 3, that is the first input, and the second input component is 2 cosine 2000 pi t, and the third input component is cosine 4000 pi t minus 70 degree. We know that filters respond with different frequency, so we need to identify the frequency for each of the component. Then based on their frequency, we should figure out what is the transfer function for that frequency. That means we need to figure out what is the amplitude change and what is the phase angle change. So let's first look at the input 1, which is 3. So for input 1, we know the frequency in fact is 0, so that we go back to our transfer function. We know that if the frequency equal to 0, then the amplitude will be 4. And if the frequency is 0, the phase angle will be 0. Then we know that for the input, which is 3, the transfer function is 4. The frequency of 3 is 0, so the amplitude is 4 and the phase angle equal to 0. So the transfer function for frequency equal to 0 is just 4. Then we can figure out the output for this component is equal to the transfer function multiplied by the input, which equal to 4 multiplied by 3 equal to 12. Then we get the output component for the first input. Then let's look at the second input. For the second input, we first identify the frequency equal to 1000. Then for the frequency equal to 1000, in the last example, we figure out that the transfer function is 330. The amplitude will be multiplied by 3, it's amplified by 3, and the phase angle will be plus 30. The phase angle will be increased by 30. Then we can figure out what is the second component for the output. The second component will be equal to the transfer function at the frequency equal to 1000 multiplied by the second input component. For the second input component, we know that it doesn't have any phase angle degree, so we know that the phasor representation in fact is 20. So the transfer function multiplied by the input in the phasor representation will be 330 multiplied by 20. Then we know it will be 630. Then we're going to figure out what is the last component, the third component of our input. The third component has a frequency of 2000. Then we can go back to the transfer function to figure out if it is 2000 of the frequency, what will be the transfer function. So for the amplitude with a frequency of 2000, it is 2. It will be amplified by 2. And the phase angle of 2000 is 60. So we know that the transfer function for the 2000 will be 260. Then we can figure out what is the output component for this 2000 frequency. We are going to use the transfer function as the 2000 frequency multiplied by the input component, which will be 260 multiplied by 1. You can see our amplitude of the third component is 1, and the phase angle is -70. So this is the -70 phase angle. Then we do the phasor multiplication. We will get our output component will be 2, -10. Then we know the sinusoidal representation for each of the output component will be for the output 1 is 12. For the output 2 is 6 cosine 2000 pi t plus 30 degree. You can see the amplitude changed, the phase angle changed, but the frequency won't change. Then the same thing for the third component. It will be 2 cosine 4000 pi t minus -10. The amplitude and the phase angle changed, but the frequency won't change. However, the change of the amplitude and the phase angle will be based on their frequency. Then we know the output signal, in fact, is the summation of all the output component, so that we know the output signal will be 12 plus 6 cosine 2000 pi t plus 30 degree plus 2 cosine 4000 pi t minus 10 degree. This graph gave us an idea what will the filter do to the signal. So here you can see if we have an original signal like this, in fact, we can separate this original signal into two signals. Of course, we know that based on the Fourier theory, for the original signal, it is the summation of sinusoidal component. So let's see, this is the low frequency component of the original signal. This is the high frequency component of the original signal. Most of the case we know the low frequency in fact is your signal. The high frequency in fact are noise. So that what we want to do is we want to amplify the signal. That is what we want. But we want to get rid of the noises. That's not what we want. Since the signal and the noises, they have different frequency, then we can design a filter. For the low frequency, we amplify the signal so that you can see the output component for the low frequency signal will be amplified. For the high frequency noises, we can reduce the amplitude so that we can get rid of the noises. Then after the signal passes through the filter, then the output will be the summation of the output 1 and output 2, so that you can see that this will be our final result. We amplified the signal that we want, but we reduce the noises that what we don't want, so that we can get the information from our signals. Now let's look at the first order low-pass filters. So as we said, the filters we are talking about in fact are circuits. This is the first order low-pass filters. It is called first order because it has the R and one capacitor, so it is the first order. And it is the low pass, means it's passed through the low frequency information. So this part, the RC circuit, this part in fact is our filter. The input signal is this Vin, which is the voltage signal, and the output will be our Vout, also the voltage signal. So we know that after the signal passes through the filter, the amplitude and the phase angle might change. Then we can determine if we want to pass through the frequency or if we want to get rid of this frequency component. This is the low pass filter, means the low frequency signal can pass through, but for the high frequency signal, it will be get rid of. When I say get rid of, in fact, means we reduce the amplitude so that we can ignore that signal. So first, we need to figure out what is the transfer function of this filter. We know that the definition of the transfer function is the output divided by the input. So that will be the output signal divided by the input signal. Then, from what we learned before, we know we can figure out what is the current. This is a series circuit, so that we can figure out the total impedance. Then use the voltage divided by the current. We can know what is the voltage divided by the impedance. We can know the current. Then use the current multiplied by the impedance of the capacitor. We can figure out what is the output. Then use the output divided by the input. We can figure out what is the transfer function. So here you can see the current will be equal to the input divided by R plus the impedance of the capacitor. Then the output will be equal to the impedance of the capacitor multiplied by the current, so that we can figure out what is the output. And the transfer function equal to the output divided by the input. Then we can figure out what is the transfer function. Then we define a FB, the break frequency, equal to 1 over 2 pi RC. You can see if we define the FB like this, then the transfer function can be written in 1 over 1 plus J F over FB. If you look at the FB, you can see FB equal to 1 over 2 pi RC. And RC, in fact, is what we learned before, is the tau. After you have the circuit, this R and C is determined. So your break frequency, in fact, is determined, is a constant. We'll talk about the break frequency later, but keep in your mind, this break frequency, in fact, relate to the properties of the circuit. Then after we figure out the transfer function, then we can separate the amplitude and the phase angle. So the left-hand side graph represents the amplitude. The right-hand side graph represents the phase angle. Then if we want to figure out what is the output, then we can use what we just learned, the output equal to the input multiplied by the transfer function. Then we can figure out what is the output. Now let's see we have a input signal. The first component is 5 cosine 20 pi t. Then what will be the output? So here you can see this will be our circuit. You have the input signal, you have R, you have RC. Then we can figure out the break frequency first. So the break frequency will be 100 Hz. And then for the component of the input signal, we will determine one by one. The first input signal is 5 cosine 20 pi t, so that we know the frequency will be 10. Then based on our transfer function, which is equal to 1 over 1 plus jf over fb, then we can figure out if the frequency equal to 10, what will be the transfer function. So in this case, the transfer function is 0.99 and the phase angle is negative 5.71. So if you look at the amplitude is 0.99 is almost 1. So that means for this frequency, the filter didn't do anything. Maybe I shouldn't say didn't do anything, but most of these signal component will pass through the filter. Then we know the output component for the first input will be the transfer function multiplied by the input, which will be 4.975, and the phase angle is negative 571. So that you know the component of the first input will be 4.975 cosine 20 pi t minus 571. And the second component of the input signal is 5 cosine 200 pi t. You can see the frequency change. Then the same thing, we are going to figure out what is the transfer function for the frequency of the second input signal. So we first identify the frequency for the second input is 100. Then based on our definition of the transfer function for the low-pass filter, we can do the calculation, and then we figure out that the transfer function for the second input component is 0.7 and the phase angle is negative 45. So the output component for the second input component will be 3.535 negative 45. So if you look at this transfer function for the second input, you can see the amplitude is 0.7. It's not close to 1. That means we reduce the amplitude of the second input component. Then we can figure out that the output for the second input is 3.535 cosine 200 pi t minus 45 degree. And the third component of the input is 5 cosine 2000 pi t. Then we know that for the third component is 50. The same thing, we are going to identify the frequency for the third input first, which is 1000. Then from the formula, we can figure out the transfer function at the frequency equal to 1000 is 0.0995. So that you can see at the frequency equal to 1000, the amplitude is almost 0. That means we reduce this frequency component. So here you can see 1000 in fact is a high frequency, most probably is the noise. Then the amplitude is 0.099, so it's pretty much can be ignored. Then if we want to figure out what is the output, we know we are going to use the transfer function multiplied by the input. You can see the amplitude of the third component is 0.49. It's quite small. Then if we combine all we have been calculated, then you can see the output signal will be the combination of the three output components for the input signal, and based on their different frequency. If the frequency is 10, most of the signal will pass through. The amplitude is 0.99, is about 1. And if the frequency is 100, the amplitude is 0.7. We reduced a little bit of this component. And the last component has a frequency of 1000. The amplitude of the transfer function is about 0.0995. So we can see we kind of get rid of this component.